This lesson has some further integration by substitution in it. So integration by substitution, obviously you've done in single maths. We're just going to apply it in some different with some different substitutions here. Now you won't always be given these substitutions, so you do need to be able to recognize these yourself. All of them are going to come from these two identities here. So either the trig identity cos squared plus sine squared equals 1, or the hyperbolic identity cos squared minus sine squared equals 1. They're all very similar, so you pick the one that corresponds to the identity. The first type are where you've got an a squared minus x squared, or it's perhaps easier to think about it as a 1 minus x squared. This looks like your trig identity, because usually you can rearrange this to make cos squared equals 1 minus sine squared, or vice versa. We're going to suggest that you use x equals sine u as your substitution, and if it's a number that's not 1, so a squared, so for example like 4, you choose x equals 2 sine u, so that when you square that you get the 4 out and you can factorize it out. You could use cos as well, that would work. So this example, find root 1 minus x squared. So we're going to use a substitution, x equals sine u. First thing to do in a substitution question is differentiate this to get dx in terms of du. So times it by du, get that dx is cos u du. Start substituting in, so your integral becomes root 1 minus sine squared u rooted times cos u du. We can use the fact that 1 minus cos sine squared is cos squared times cos u. And here root cos squared is obviously cos, times that by the other cos gives you cos squared u du. This is an integral that we know how to do now, so the way to do this is to use the double angle formula for cos. So cos 2u is 2 cos squared u minus 1. Rearrange this to make cos squared the subject, so add the 1 and divide by 2. Get a half cos 2u plus a half. Substitute this into your integral, so that's now integrating a half cos 2u plus a half. Integrating cos 2u goes to sine, and we need to divide 2 by the 2 in front of the u. Integrating a half goes to a half u plus. Finally, we need to turn this back into terms of x. So we can rearrange x equals sine u to make u the subject. Okay, u equals plus sine x, and I can sub that into the half u, but I don't want to substitute that into the sine because that's just messy. Instead, what I'm going to do is use my double angle formula for sine to write it as 2 sine u cos u. Now sine u will just swap for x. We need to write cos in terms of sine, and we can use the identity cos squared plus sine squared equals 1. As well. To write cos u is 1 minus sine squared. If we swap all that in, so quarter times half, 2 gives me half. Half sine u, and cos u I said I can write as 1 minus root 1 minus sine squared u plus the half u. Now I can substitute x in instead of sine u, and I can substitute inverse sine x instead of u, and this is my result. Now for the second one, it's got a plus instead of a minus, so we can't use cos squared plus sine squared equals 1 because it always rearranges to 1 minus squared sine squared. But instead, this time we can use the hyperbolic identity, because the hyperbolic identity is cos squared minus sine squared equals 1. And if I've got a plus, what I can do is take that sine squared across. So I've got 1 plus sine squared u, which is kind of the form that I want. So the substitution we're going to use is sine u to turn it into a cos squared u. So that x equals sine u in this case. Again, first thing to do, differentiate this. So dx by du equals cos u, and I can rearrange to make dx the subject. Cos u du. Let's start substituting into our integral. 1 over 1 plus x squared, so it's 1 plus shine squared u, so 3 over 2, times dx, which is cos u du. 1 plus shine squared, I can write as cos squared. 3 over 2 cos u. Dealing with these powers on the bottom, so times them together gives you cos cubed times cos u. And now I can cancel one of these to give me 1 over cos squared u. To integrate this, I'm going to write this as sec squared du, because I know that sec squared integrates to give me tan, just like how sec squared integrates to give me tan. Now I need to turn this back into x. So to do that, I'm going to write tan as shine over cos, because shine is just x. Cos, I can use the identity to write that in terms of shine. So if cos squared is 1 plus shine squared, I can just square root that. So rewriting this in terms of shine gives me shine u over root 1 plus shine squared u plus c. And then swapping the x is shine u. Gives me x over root 1 plus x squared plus c. The third type is x squared minus a squared. So again, we're going to use the identity that cos squared minus shine squared is 1. But this time making shine squared the subject gives you cos squared u minus 1. So because the x is first, I can let x equal cos u in this case and do the substitution. I'm going to do the substitution of cos u because I've got x squared minus 9 here. Because it's not 1, I need this now to be 3 cos u. So a squared is 9, so a is 3 in this case. Because when I substitute this into the x squared, I'll square the 3 and end up with 9, and then I can factorize that. I need to differentiate this, so dx by du gives me 3 shine u. So rearranging this for dx gives me 3 shine u du. At some stage in this question, I also need to deal with my limits. So x is 5 is my upper limit. And I need to work out u for this one. So subbing x is 5 here, so 5 is 3 cos u. So cos u equals 5 over 3. I want the exact limit, which unfortunately calculator doesn't give. So if you use the ln definition for inverse cos, you get ln x plus root x squared. And this gives you ln 3 is your f. When x equals 3, you get 3 equals 3 cos u. So cos u equals 1. And this has the solution that u equals 0. These are your new limits. Let's start summing everything into our integral. So our integral now is between ln 3 and 0. X, we've got 3 cos u, so squaring that gives me 9 cos squared u. And it's 9. And that's times by 3 shine u du. I'm going to factorize out the 9 from the 9 cos squared minus 9 and square root that, so that gives me a 3. And outside 1 times 3 shine u du. Cos squared minus 1 is shine squared, and if I square it that gives me another shine. I've got 3 times 3, so I'm going to times this to give 9 and pull it out to the front. And so I've got shine times shine, so this is shine squared du. Integrating shine squared works the same as integrating cos squared from earlier, so we're going to use the identity for cos to u, which is 1 plus 2 shine squared u. Remember, to work out identities for hyperbolic, you take the corresponding trig identity, and if there's a sign squared, you change the sign on that. Making shine squared the subject, so I minus the 1 across, and divide by 2. So a half cosh 2u plus a half. And then sub that into my integral. Integral of ln3 0 half cosh 2u plus du. I can now integrate this. So integrating cosh goes to shine, and I need to divide through by the 2 in front of the u. Integrating the half integrates to u. So that should have been a minus function. Minus, and we've got ln3 and 0 as my limits. Sub those in, so quarter shine over 2 ln3 minus the half ln3. If you sub 0 into this, you will get 0. So shine of 0 is 0. Obviously, subbing it into u, so gives you 0. A quarter shine to ln3 you can do in your calculator. That will be 10/9 minus a half ln3, and then just expand it out with the 9 to be 10 minus 9/2 ln3. Some trickier examples here. So this first one integrates x arctan x. It's two functions multiplied together, so we're going to use integration by parts on this. Now your instinct is to choose u equals x to differentiate and get rid of it, but we don't know how to integrate arctan x. So instead, I'm going to choose u equals arctan x and dv by x equals x, because I have the result of differentiating arctan x on the formula sheet, which is 1 over 1 plus x squared. Integrating x integrates to a half x squared, and then we can substitute this into our integration by parts form. That's u times v, so half x squared arctan x minus the integral of v times d by dx. Now this here, I can factorize the half up to the front. This fraction here, to be able to integrate this, I need to do some short division on this. X squared of x. I'm going to rewrite the top as x squared plus 1 minus 1. So now I've got the denominator up there, and I can split this up into x squared plus 1 over x squared, which is just 1, and then minus 1 over x squared. Pulling that half up to the front and integrating 1 minus 1 over x squared. That's right. Integrating 1 just goes to x. Integrating 1 over 1 plus x squared is on your formula sheet. It integrates to arctan x and then plus. Now to integrate sin x, I'm going to use integration by parts again. This is very similar to integrating ln x. So we don't know how to integrate arctan x, but we do know how to differentiate it because it's on the formula sheet. So what I'm going to do is I'm going to write this as 1 times arc sin x, and then use by parts on this. So if I let u equal arc sin x, because I know how to differentiate it, and let dv by dx equal 1, I can differentiate arc sin x to give me root 1 over root 1 minus x squared, and I can integrate 1 to give me x. Sticking this into your integration by parts, you get u times v, so x arc sin x, minus the integral of v times u by dx. Gives me this. Now integrating this here is a reverse chain rule. So I'm going to rewrite this as x minus x squared minus a half dx. So what I noticed here is that if I differentiate the inside, I'll get minus 2x. I've already got the x on the outside, so I just need to deal with the numbers. To make it minus 2x, I'll times it by minus 2. I can't just randomly times it by minus 2, so I have to divide by minus 2 or times by minus half to kind of cancel that out that I've added in. This integral now, so the minus 2x I could ignore because it came up because of the chain rule. All I've got to do is add 1 to the power and divide by the new power, so divided by half, so it's times and by 2. I've got the minus half out the front, which turns into plus a half x sine x plus the, and your half times 2 obviously cancels out, so we get half sine x sine x plus 1 minus x to the half. Final example, so use a substitution x equals shine u to do that integral. So it gives us the substitution this time, which is nice. So differentiate this to get cos u and write dx in terms of du. That's substituting into your integral, so x squared is shine squared u over shine u squared u plus 1, and dx is cos u. On the bottom, shine squared plus 1 is the same as cos squared. Du. Root cos squared is obviously just cos, and it will cancel with this cos over du. So you are now integrating shine squared. We've done this a few times already, so we're going to use the double angle formula for cos. 1 plus 2 shine squared u, so same as the trig one, but change the sign because of the shine squared. So shine squared u is half cos 2u minus half. Substitute that in, so half cos 2u minus half u. We can integrate this now to give us a quarter shine 2u minus half du. We need to turn it back into terms of x. So x is shine u, remember? X equals shine u. U equals inverse shine u x. Sorry, or you could use the ln definition if you like. Shine 2u, we need to use the double angle formula for that. So shine 2u is 2 shine u cos u, same as. So that's plus the from 3. Cos, we're going to write as root 1 plus shine squared in this case, and then we can start turning it into x. So we've got a half x instead of shine u, root 1 plus x squared instead of cos u, and minus a half shine to minus 4 of x plus c. I can use the ln definition. Hence find this integral. So we've just shown that integral there. So hence find x r shine it. So we're going to use by parts on this. I need u and dv by dx. So I'm going to choose u is r shine x. dv by dx is x because I don't know how to integrate r shine, but I know how to differentiate it. Du by dx is on the formula sheet. Just need to look up. Differentiate r shine. Differentiating r shine is 1 over root 1 plus x squared. Integrating x to half x squared. Stick this into the formula. So you get u times v, so half x squared r shine x minus the integral of v times du by dx, which is a half x squared over root 1 plus x. We've done this integral in the first part, which is why it's a hence question. Half x squared r shine x minus half times the result that we got in the previous part of the question. So that's a quarter x root 1 plus x squared minus a quarter r shine. This was r shine instead of inverse shine. X plus c.